This video is going to cover statically indeterminate beams. Statically indeterminate means that it's not solvable with statics. Statics is solvable when the number of unknowns and the number of equilibrium equations are equal or less. So indeterminate means that this time the number of unknowns that we have is greater than the number of equilibrium equations, meaning that no matter how you try to solve for it, you won't be able to, because you have, say, 4 unknowns, 3 equations, and the best you can get is in terms of 1 unknown for every single force. So we need to be able to solve for one of them. And how we're going to do that is we're going to use superposition. So we're going to take our situation that's statically indeterminate. We're going to remove a support. If that one support was removed, now it's statically determinate. So now we can find our deformation or deflection, whatever you really want to call it. Deformation can be things like axial deformation, thermal deformation. Angle of twist is technically a torsional deformation. However you have deformation, or we can talk about it in terms of deflection for beams and shafts. We're going to find the deformation with that support removed. So pretend that just that extra, probably a roller that was thrown on, remove it. And now, what's your deflection or your deformation? Then we're going to create a new free body diagram. And this time we're going to remove the loading. So unload the whole member. And instead of that support that you had before, replace that support that you removed, the extra one, and put it as a point load instead. Then you just need to solve for the force that's going to create the same deformation or deflection that you had from before. Because if you think about it, all that's really going on in a statically indeterminate system is that you put an additional brace to prevent motion. So, for instance, you had a support, you had an additional roller, and you really didn't need it. And the whole reason you put it here is so that the deflection at this point was 0. That's what you did. So, effectively, you remove the support, you watch it deflect, and then you come back and you brace it at that spot, which the brace is simply a point load going in the opposite direction. And that point load has to create the same shape as you had before. Once you do that, you effectively can solve for what that force is to make that overall sum of the deflection 0. And once you have the support force, well, now it's statically determinate. Because now you have 3 remaining unknowns and 3 equilibrium equations. So now you can just solve for it. That's the premise behind our statically indeterminate system. So for this one, we're going to make it a little bit more fun than that. Now we have a fixed end and a roller. Again, you can argue it's like kind of a common thing to just throw on an extra support just because you don't want deflections, right? So we have a fixed end and we have a roller. And we have this linearly distributed load. And we want to find the reactions at A and B. So yes, statically indeterminate, there's going to be 3 unknowns at A and 1 at B. So a grand total of 4 unknowns and only 3 equations of equilibrium. Some of the moments, some of the forces in the X, some of the forces in the Y. So not solvable. So what we're going to do, step by step here. Step number 1, we said was remove the support. So I'm going to remove the roller. So here I have my 5 kips per linear foot as a linearly distributed load across 12 feet. So what I need to do now that I've removed it is find the deformation with the support removed. And again, what point do I want to find? Obviously, I want to find deformation at the point where the roller is going to be, so I need to find it here. Conveniently, when I go to the back of the book and I use the appendix, this is usually going to be Vmax. However, when you go to the appendix, you realize that that's not a loading situation that you have. So we got to get creative, right? In order to use the ones in the back, we got to get real creative with what we're looking at. So we're going to use superposition to try and create this loading situation. I'd like to think of it a lot less in terms of forces and a lot more in terms of just shapes. If I want to get a triangle going this way, if I look at what I have in the back, what can I add together to make it that direction? Well, how my brain works is I've got a big rectangle, and if I want the triangle on this half, then I take a really big rectangle and I remove this half. Okay, so what does that actually mean for us? That means I'm going to have a rectangle, ta-da, and again, this same height here, correct? So that's going to be 5 kips per linear foot. So I have my rectangle, which is a uniformly distributed load of 5 kips per linear foot. And I'm going to remove the other guy. Well, to remove him, I'm going to add him, but going in the opposite direction. So I can just draw him underneath, going that way. You can have his arrows going up. It doesn't really matter either way. I like to, when I draw my arrows up, I like to come from below, as I feel that kind of helps the visual a little bit more. So if you combine those two pieces, we're effectively looking at this situation, and we are left with the guy that we want. And again, the height of this dude is still 5 kips per linear foot. How magical. So that's how I get my load to look like the red one. So again, I'm going to find the deflection at this endpoint. And conveniently in every single one of my equations, that is V max. So my V at point B, for the one in green here, using those lovely equations from the back of the book, we're going to get that it is minus WL to the 4th divided by 8 EI. The minus, of course, meaning that this is going down. Okay, so I plug it in. I have minus 5 kips per linear foot, and L is a grand total of 12 feet, we said, raise it to the 4th, divided by 8 EI. The number I'm going to get for this, if I just kind of shrink it down some, is minus 12,960 divided by EI. Okay, now for my blue one. So for the blue guy over here, he's pressing up, so my deflection's actually going to go up. So this time, when I get my deflection at point B, up is positive. So where on the table you read negative, remember that you have to go the opposite direction because your arrows are going the opposite direction. So we have a negative of the negative WL to the 4th divided by 30 EI. So again, negative, negative, going to become positive here. So W is 5 kips per linear foot. L to the 4th, we have 12 feet raised to the 4th here, divided by 30 times EI. And I'm going to get VB for this one. Again, he's positive. He is positive 3, 4, 5, 6 divided by EI. So my total, should probably have written it in the correct color, right? My total here for my deflection going down is going to be the green one plus the blue one. So my total VB for the red guy is going to be the green one, who is minus 12,960 over EI, and then plus my blue one, who is 3, 4, 5, 6 over EI. And what I'm going to get for my answer for the total red force is going to be minus 9,504 over EI. And this should make sense. I am going down, correct? If you look at that picture, obviously it is going down, and it's going down by not as much as a full uniformly distributed load. So cool. So that was step 1. Oh, and technically, this part here was step 2. Find the deformation or deflection. Cool. Step number 3, we said on a separate free body diagram, I unloaded. So here's my new free body diagram. I've unloaded it. And now I'm going to replace the support I removed last time with a point load. And remember, this point load has to resist the deflection. So before we said the red guy was going to be going down. So we need to be pressing up in order to resist it. And those two we can add together and they should equal 0. So this support force is By. So again, we just go to the back of the book, we look at it, and we have a nice equation for this. So the deflection at B for a point load at the very end is technically minus, but we're going to have to put a negative on that because we're going the opposite direction. So it's PL cubed over 3EI. Ta-da! And so we're going to plug in some stuff. We have the minus and the minus become positive. We have P. We don't actually know P. He's By. Then we had 12 feet cubed divided by 3EI. Okay, so ta-da! My deflection at B for my new point load is 576 times By divided by EI. So remember, these two have to counteract each other. So by that we mean, in step number 4 here, we're going to solve for that force. So the sum of them has to be 0, which means our 576 By divided by EI plus our red one, our load, who is negative 9,504 over EI, have to add together to equal 0. Which is why usually you'll see it written as something like 576 By divided by EI is equal to this guy having his sign reversed. 9,504 divided by EI. So in case you're wondering why you might see it as they just set them equal and disregard sign, is because technically I am adding them together to equal 0. And because of this, you can multiply both sides by EI, and 0 times EI is 0. So yay, so EI goes away. And then if we want to find By, it is simply 9,504 divided by 576, which is 16.5 kips. And it is in the direction we assumed, which is going up, obviously, to resist that downward force. So now that I've found By, all I have to do is go back in step 5 to my original picture, right? And this time we had our 5, that was pretty long. We have our 5 kips per linear foot on our linearly distributed load here. And By, ta-da, here he is, 16.5 kips. And we did say that was 12 feet. Last thing we want to solve for, AY, AX, and the moment at A. But this is now just statics. So if you sum the forces in the x direction and set it equal to 0, lo and behold, you get AX and only AX. That's cool. If we sum the forces in the y direction and set it equal to 0, you're going to have AY going up. You have the 16.5 kips going up. And then we have this minus the linearly distributed load. And I know it might have been a bit since you've seen linearly distributed loads, but remember it is the area under the loading diagram here. So the area of a triangle is 1/2 the base of 12 feet, the height of 5 kips per linear foot, and that's going to give us an AY equal to 13.5 kips going up. Ta-da! So not quite as much as By, because obviously By is taking more of the load. Then we can sum the moments about point A, set it equal to 0. And we're going to have moment A. AX and AY don't create a moment, and then we have our distributed load here. He's going to be going the wrong way for us, so minus. Remember, it's force times distance. The force is the area under the curve, so 1/2 the base of 12, the height of 5 kips per linear foot. But then we have to multiply by the distance of his centroid to our location, which for a triangle, going the long way, is 2/3 the distance. So times 2/3 that distance of 12 feet. That's how you get kip feet. And then we also have BY in here. He's going to be going positively about our point A. That's 16.5 kips times his distance, of course, 12 feet. So plugging that into the calculator, and we're going to get that the moment at A is equal to 42 kip feet, going the direction we actually drew it. So cool. So you can see it's not actually too different to solve for our statically indeterminate system. You just, again, you got to get creative with your superposition. But once you get creative with it, you find one force and la-di-da, there you go. So again, and it doesn't just have to be deflection, it can be deformation. Deformation can be things like PL over AE if it's axial. It could be that it's equal to alpha times delta T times L if it's temperature. It can also be angle of twist, which was TL over JG. Okay, so there's a lot of different types of deformation that it could be. It could also just be deflection. So keep that in mind when doing statically indeterminate systems.